Hey, good evening, everyone. You guys hear me? I saw some of you sitting in the classroom. Fanze, are you sitting in the classroom? No, you don't need to close your cam. No need. You can open your camera. That will make me feel more real. I mean, if you guys wish, you can open your camera, but mute yourself. That doesn't hurt. Yeah. Okay, I saw someone joining, so give me more time. I don't think so. You don't need to decide your project this week, but you need to decide your team this week. Yeah, that's fine. Yeah, so basically, no need to decide the topic, but you need to decide the team and ask a representative to send me your team information. Did I set the deadline? I don't think I have the deadline for this one. Yeah, thank you very much if you do that. Well, if you did that. Yeah, how about we start right now? I think it's a good time to start. When is the deadline of the project decision? Good question. I think it's in between your team. My opinion will be the earlier the better. So once you determine the topic, you know which way, which direction you are going to go. It seems no voice. No, I have voice. Can you guys hear me? Hello? Yeah, I think yeah, probably your speaker has some problem. Yeah, so I don't think I set the deadline for topic. So but I would say I encourage you guys to fix the topic ASAP, so that you guys know the way that you are going to work on, the way to go, the topic you like to work on, and also you will work on starting collecting data, collecting information, and probably planning the methodologies, and also what are the results that you expect to see, and so kind of. Let me see. Yeah, it's already 7:05. So I think we can start our lecture today. If we have new students, I mean, few more students joining in, then I will admit when I talk. All right. So in previous class, we did actually conceptual understanding about the current different initiatives of smart cities in different regions in the world. we also talk about some main features of the smart city development. The main features means the different advancement of the part of the city. Okay, so we talk about like sharing economy. We talk about smart building and energy and transportation systems, intelligent transportation, and so kind of. So we know that smart city actually has a very large scope. But in Hong Kong, its definition is actually 6 pillars, including the mobility, living, environment, people, government, and economy. Okay, so that's the major 6 application fields that the AI and data science will be applied into. Yeah. Yeah, so we probably stop here. We finished the sharing economy last week. Today, we are going to talk about the 2 key technologies involved in the smart city development. One is called cloud computing, another is called Internet of Things. Okay, they are actually major technological thrusts that need to be developed in order to support the operation of a smart city. So first, let's talk about the cloud computing. Okay, so why we say cloud computing and Internet of Things are so important in a smart city? So if you look at all the recent applications of AIs in your life and any advancements of your life, like driven by the new technologies, they are basically have some of the common characteristics. One is they need to have an end sensor or end channel to collect information. So this information collection is not like collect like private information or so kind of, they want to check the dynamics or change of the whole system over time happened in every places in a city. Okay, so it's like the city needs to have eyes, needs to have noses, needs to have ears to see, to smell, to hear, or to listen, to perceive informations from different dimensions. So how to enable the city have the channel to communicate with the reality, okay? So you need to rely on a huge number of sensors. They could be security cameras. They could be temperature sensors, motion sensors, LiDAR sensors, and so kind of, okay? They are sensing the environment, sensing the changes, sensing the passenger flow, and sensing different current, okay? Measuring the electricity consumption, and so kind of. So once the information are sensed, collected from every corner of the city, then they are fused in the center. And all the information will be fused in the center and do computing there. And that is called cloud computing. But cloud computing actually can mean much more than that. Okay, it's not just centralizing all the information together doing computing. It means more on the service side. Cloud computing is a kind of can be counted into a kind of sharing economy mode. Okay, then I will explain the analogies between the sharing economy and cloud computing in a later. So if we look at the cloud computing technology itself, we will see that I don't know whether you guys still have memories when you were born. Any of you use very old version of Windows, like Windows 98, Windows Vista, or any of you have experience of that? Or any of you have buy the disks to install software in your computer? No? None of you have experience on that? Or download a copy of software and install in your computer? Have any of you have such kind of experience? You can reply me via your chat box, or you can directly speak. Maybe. What does that mean? Maybe in primary school, that's good. Yeah, maybe Windows XP. Yeah, that's right. Yeah, in the old days, the distribution of all these software, they are distributed via copies. And those copies are contained in disks. And later, they are actually kind of program copies maintained in a hub that you can download from the internet. Okay. And in the old time, the internet speed is not that high. And we don't have like a commonly deployed broadband. So any of you use like a BitComet, the BT, which is kind of P2P software, sharing like the download speed and resources and so kind of. I bet some of you might have touched, but might not everyone. So you will see that in the old days, all the applications or the applications actually nowadays we call applications, but in the old days we call softwares. Okay. So different softwares are distributed via the other media, like disks and something like a physical. Okay. And later they changed to kind of downloading channel from the hub. But still, such kind of mode have a lot of problems. Okay. And one important problem is the version of a software or a version of the app. Okay. Why the versions of software and why the versions of app? So when you develop a software, you might have a lot of bugs. Okay, you need to debug, and you might not have the perfect version at the beginning. But you need to sell it, distribute it to the customers to get some, reward. I mean, the refund of your investment. Okay. So you might release a beta version, and you might find out some bugs or find out some malfunctions in this software and receive feedbacks from the customers. Then you have to come back and fix those bugs and release a newer version. Okay. But to distribute those newer version, people usually use patches. Okay, to update the software installed in the computer. But this is very inconvenient because not everyone will enjoy the patches. Some people might not just download it. Okay. But the cloud computing, its innovation is that you just need to maintain the interfaces of the end users, and the software service is located in the cloud. And every time the usage of the software, they are interacting through the high-speed internet. Okay, so customers interact with the interfaces, and the interfaces will send a request to cloud computing, and then the response will be delivered back to the end users. Okay, so the good things is that you can do anytime updates of the applications on the cloud. That saves a lot of cost. Okay, so many applications nowadays, they are actually cloud-based. And in cloud computing, internet services are just channels for accessing those applications. And all the website or web-based interfaces, they are just serving for the interaction between the resources held in the cloud as well as the end users. Okay. So there will be a unique advantage that you can better protect your core techniques because you didn't distribute your code or your software to the end user. They might not see the code, or they might not do the decoding or inverse engineering of the software. Okay. And also, it is easy to maintain, and it has a more flexible business model than one typical successful model is the licensing model. Okay. So I remember in the old days when I used the Adobe Reader, or nowadays a more advanced version called Adobe Acrobat. And what I need to do is to pay on one time and buy the software Acrobat and install in my computer. And nowadays, business model changed. They charge me the licensing fee. That means every year I need to pay for it to enjoy the latest version. Okay, so that sometimes could be in total more expensive. But if you check the usage period, that means probably this year you want it and next year you don't want it. You can save money. Okay, you can make a more flexible decision. So good or bad, okay, it really depends on the different feeling of the different user. Then what is cloud computing? Cloud computing is a very general term, okay? This is utilized to describe a new class of network-based computing services that takes place over the internet. So internet is the foundation for for having the cloud computing born, okay? So basically, it's a kind of transforming the computing like utility usage, okay? It enables a kind of new business mode in computing service, and it mimics the utility. The utility means the electricity, gases, okay, consumed in your home. You need to pay electricity bill every month. You need to pay the water usage bill every month, as well as the gas fee every month, okay? So computing service actually move that one, okay? And also enables a collection of integrated and networked hardware, software, and internet infrastructure, okay? So to enable a cloud computing service, you need to build up infrastructure which integrating different hardwares, and you need to install a huge amount of softwares, and you need to have the internet to access out to different end users, okay? And sorry, going too fast. And using the internet as the communication channel. So the internet will actually serve as the transportation for providing those hardware. So what does the providing of hardware mean? That means they will provide you some hardware resources if you request some computing task. Okay, if you want to conduct some computing tasks, you don't need to have a physical computer sitting there. You just need to have an interface. You can use either your iPad or even your phone to access some cloud computing services and to execute the programs and computing tasks there. And it also can provide software as well. Okay, nowadays quite many software, they are actually cloud computing. Okay, and also networking services to clients. You can request cloud resources to hold your website or your sharing resources so that clients can access them. So the good things is the cloud computing platforms, they hide the complexity and details of the underlying infrastructure. So every users or even medium users, they don't need to know the complexity and details of the techniques behind it, okay? And applications by providing very simple graphical interface or API. So what they provide you is just an interface, okay? Or an API is a kind of programming interface that you can access data and transmit your command. And from the business aspect, the cloud computing platform provides on-demand services. That means you have demand, then you request a service, then you pay, okay? And such kind of service will be always on and anywhere, anytime, and any place if you have internet. And the cloud computing nowadays, they are more like a pay as usage. Very flexible. You pay what you request, and this request can be changed over time. So that means your request, your demand, your request of computing resources or software services can be scaled down or up in terms of different capacity and functionalities over time. Okay, and the hardware and software services are kind of available to general public, enterprises, corporations, and business markets. So cloud computing is actually umbrella term. Okay, it refers to different internet-based development and services, but there are a number of characteristics to define kind of cloud data in application services and infrastructure. So first, the cloud computing services will be always remotely hosted. Okay, so no matter the services or the data, they will be hosted on a remote infrastructure, and you usually cannot download it. Okay, and ubiquitous, the services or data are available from anywhere. You can access them, but the downloading of those resources might require extra costs. Okay, and such kind of access of the resources, they are commodified. So they are kind of commodity. Okay, so the result is a kind of utility computing model, which is similar to the traditional utilities, like what I have said before, like gas, electricity bills that you pay every time. And this figure actually shows the general architecture of the cloud. So at the bottom, they are the infrastructure. Okay, and those infrastructure can also be part of the cloud service. They will say kind of infrastructure as service. So some people are not interested in just using the interface or using intermediate part. Some people are interested in the infrastructure. For example, some startup companies, they don't really want to invest a kind of million Hong Kong dollars or such kind of scale expenses on setting up a new machine, and they also need to recruit a person to particularly maintain those machines. That could be a huge amount of cost and less flexibility, because those machines they're sitting there, they their values degraded every year. Okay, so what they want is they want to have some hardware to support their services, but they don't want the physical thing. So they consider a way of renting those hardwares. So providing hardwares to some customers is kind of infrastructure as a service. So this is the bottom layer of the cloud architecture. And the second one is called platform as a service. It's a kind of intermediate between the software as a service. The platform as a service means it's not just the pure hardware resources. They also provide you some computing platform. It can include some of the softwares packed inside this platform for you to do the application development and to host some web services or internet services and so kind of. And the top layer will be kind of software as a service. It's kind of access to the individuals, and it's kind of core service value nets. So cloud architecture actually includes 5 components. If we look at the infrastructure, the hardware side, the computing devices include the computer, a network of computers. And this network of computers, or sometimes we even say it's like it's kind of customer end devices. Okay, it's like the smartphone in your hand, the iPad, your laptop, okay? So this part, computer network, they are connected via internet. They are servers and data storage system. Servers doesn't necessarily mean data storage. Server can mean the computing devices integrated as a system and storage as a separate one. But sometimes people will regard these two together as one as well. Doesn't matter. And different applications, different softwares, and the services you configure based on this cloud architecture. So it is a sharing company because it shares a pool of configurable computing resources, and it offers on-demand network access and provisioned by the service provider. Okay. And the common characteristics in cloud computing. There are 8 common characteristics in cloud computing. One is massive scale. So cloud computing services is massive scale. It aims to serve a massive scale of customers. Its service is resilient computing. What does resilient computing mean? That means its service needs to be maintained consistently. Once the service is broken down, it needs to be recovered very soon. Okay, this is called resilient computing. So if your cloud service is a kind of that people use your service and broken up for a very long time and cannot re-access it, you will be never used again. Okay, people will not visit you again. Homogeneity. You will have homogeneous versions of services, access to different customers. Okay, and if people request the same scale of services, their services standard is the same and the content is the same. The fourth one is the geographical distribution. So you are able to distribute your service via the internet to different places geographically in the world. And virtualization, all the physical machines and services, they are virtualized. People cannot touch the software, the hardware, okay? They can use the internet to visit, to access them. Cloud computing is service-oriented. So the service quality is quite important. So you aim to supply a very reliable cloud computing services. And low-cost software. The low-cost software means people are actually sharing the software so that the cloud computing resources, when they buy this software, they can use a lower price. They actually have a lower price. Okay. For example, you can pay to Adobe Acrobat, say, I pay you $50,000 per year license fee, but I can distribute this software to millions of people, and each person, they probably just spend $1 in the cloud computing services. But anyway, it's a kind of concept, but they do have a financial model to computing to determine the prices. And advanced security is every cloud computing services provider, they have the hardware infrastructure, they maintain the software side, they do need to recruit a very professional team to maintain their cloud computing services, their infrastructure not to be attacked by the hackers, okay? And there are 5 essential characteristics in the cloud computing. They are very important characteristics. One is the service is a kind of on-demand self-service. You need to determine the configuration you want to request, and people will determine the price for you. And to enable the cloud computing services, everyone needs to have a broad network access. The speed needs to be high, otherwise your access can be quite slow, then the experience will be pretty poor. And rapid elasticity means the service can be changed very rapidly once you send a request, and the configuration of the service can be immediately changed. Resource pooling, that means they actually a kind of sharing economy mode. All the infrastructure, hardware resources, and software resources that are put together and shared to the end users. And the service is able to be measured so that they will have the unit of charge for everyone. So cloud service models, I actually already talked about it a little bit previously. They are kind of SaaS model, it's called software as a service, PaaS model, platform as a service, and IaaS model, that's infrastructure as a service. Okay. So this is a kind of a little bit old. So a lot of companies, they have already expanded to cover all types of services. But in general, we can summarize that the infrastructure as a service, they basically provide the hardware, okay? And the platform as a service, they can provide the hardware, and they can also have some platform development so that they can provide a computing platform to different users. And software as a service, that's a very advanced service model that you offer the software to different end users via the cloud computing mode. And here we use a two-dimensional grid, 4 cells, to evaluate the maturity model of the software as a service. Okay, so software as a service can have different configurations of different levels. So they can correspond to different maturity levels. So the level 1 is called ad hoc customer one instance per customer. Okay, ad hoc means you need to do customization, and the customization is done based on each of the customer's requests. Okay, that's purely customized. But that causes a lot of trouble because you need to customize. That means you need to serve individually. You need to spend a lot of energy. Okay, and the level 2 is kind of configurable per customer. That means you have some examples for different customers, or a number of examples for different customers. Okay, so usually it's kind of the same example, the same configuration for different customers. The level 3 is called configurable multi-tenant efficient. That means you can change for different customers as well. And the last one is called scalable, configurable, and multi-tenant efficient. Scalable means you can scaling up and down for different pool of customers. Configurable, that means you can, according to a pool of changes to configuration, or just one of them, their request to do change of the configuration, and so on. So that means you have kind of mass customization capability. It's more efficient. And the cloud computing services can be described as different layers based on their focus. So the bottom layers, they are more infrastructure focused. That means you host, provide some hosting services, storage services, and even offer some platform. Okay, and the application focuses will be ranged from the services to the development. Okay, services just like offer different applications, even offer different softwares, and people will directly use those softwares. It's like using Alipay or using PayPal, and so they are kind of services via application. A second level application means development applications or hold applications. Okay, and the third is development. That means you develop softwares on the platform, okay, and build up the cloud for those developed applications. And some further details about the basic cloud characteristics. The first one is, as I said, is called no need to know. This no need to know is in terms of the understanding the details of the infrastructure, okay, and the application interfaces with the infrastructure via the APIs. So you don't need to understand the underlying details of the infrastructure. And you just need to have the application interface with the infrastructure, and you don't need to know the APIs. You know, this no need to know is kind of relative, depends on what kind of users you are. If you are just directly using the apps, you don't need to know how the apps is developed and how the app is hosted, and even how the details of the infrastructure should be. But if you are working on some developing of some software, then you don't need to know about the back-end infrastructure, but you need to know some of the platform, okay? And the flexibility and elasticity always allow these systems to scale up and down as well, utilizing the resources of all kinds. The scale up and down in terms of the CPU requested, the storage size, server capacity, and the load balancing and databases, and so kind of. So we have talked that the business mode is pay as you go. It's can pay as much as you use and need it. And this service needs to be always on, anywhere, anytime, 7/24. Okay. So clouds are transparent to users and applications. So they can be built in multiple ways. It's like branded products, proprietary open source, and hardware, software, or just off-the-shelf PCs. So in generally, they are built on clusters of PC servers and off-the-shelf components, plus open source software combined in-house application and system software. So let's look at further a little bit more about the software as a service. So software as a service is a model of the software deployment. That means the software will only deploy it in the cloud. Okay. So the application is hosted as a service which will be provided to customers, access it via the internet. So the great advantage is the software as a service actually reduce the burden of the software maintenance and support. So you don't need to have in previously all the time, you need to have special software engineers to visit every customer's home, figure out why the software cannot install in their computer, okay? And why the computer cannot run the software smoothly, and so kind of. But on the other side, the customers or the users also lose something. First of all, they lose the control. You have to pay when you use it. But in the old days, the old software that contained in the disk, you pay one time. You can install the software back into your computer anytime you want. But this is no longer the case nowadays, because even your operating systems is upgraded and a lot of the old softwares cannot be installed anymore. It's not very well downward compatibility. So if some people like some particular version of the software, it might not be happen in the SaaS mode. That means the version of the software will be automatically updated after maintenance. So you cannot choose which version you particularly like. Normally, I bet if you have sufficient money, you request such kind of service, you will also be allowed. But normally, like people update the software and a new version will be released. And other terms is like platform as a service, infrastructure as a service. We have also talked a little bit about it. So the cloud computing is actually developed or further extended based on the previous virtual machine concept. It's kind of virtualization. Okay. So such kind of advancement of the information system. So we're able to have a virtualized stack, which have the hardware as the bottom layer, and they have a hypervisor to supervise the utilization of the hardware resources and creating different virtual machines containing operation systems as well as the apps. It's like the figure on the bottom, right bottom. Okay. So the virtual workspaces means it's a kind of abstraction of an execution environment. That means operating system that can be dynamically available to authorized clients by using well-defined protocols. And you also have resource quota. You need to request the resource quota for your cloud service or for your virtual workspace. It's like how many CPUs you want from the hardware pool and the memory size. They will also help you to configure the software you want to. They will help you to install the operation systems that you would like. You can install Windows, Ubuntu, or kind of Mac OS and so on, and provide those services based on those operating system. And to implement on the virtual machines, it's a kind of abstraction of a physical host machine. The virtual machine is kind of a virtual representation. It's not a physical machine. It's a representation. It's a kind of abstraction. It has almost all the function from the virtual side, but you don't see it's exactly how does it look like. It does not have a kind of tangible shape you can touch or you can see. And the hypervisor actually intercepts and emulates instructions from virtual machines. So you have virtual machines, it's like your virtual computer. You interact with the virtual computer, actually making demands, request different services. And the hypervisor actually help you to further communicate your request, okay, and to the hardware, and it also allows the management of the virtual machines. And one very famous is called VMware and also the Xen system. And it also provide infrastructure API, and those APIs are supported to access those hardwares and to fetch those resources. Okay, so I guess I will temporarily stop here. Any questions and comments about the previous slides? Yeah, so basically the cloud computing or the cloud computing platform is a kind of further expansion of the old days virtual machines on the server. But such extension is not just directly copy such kind of architecture and scale it up. It actually expands and also develop some new functions in terms of the architecture. Okay. But we still need to talk about some of the virtual machine, how the virtual machines happened, and what is its architecture. Okay. And this is basically describe the back-end principles of how cloud computing can be realized, and the flow of realizing the system process of realizing such kind of cloud computing services. Okay, so I think we will stop here and we come back at 8 to continue. Okay. Okay, I guess let's continue. All right, so we talk about the fundamental concepts, the virtual machines in the cloud computing. Actually, the virtual machine techniques form the foundations of developing the cloud computing. So the VM technologies actually is initially aims to allow multiple virtual machines to be conducted on a single physical machine. Okay, so that means you have a server, which is very powerful. You want to cut the resources to different chunks and make each chunk to serve each of the clients. So the whole architecture will be like this. You have a hardware that is probably the server. Then on top of the server, you have a software, a platform called hypervisor. So the software could be Xen, could be VMware, UML, Denali, and so kind of. So based on the hypervisor, which is able to emulate a number of virtual machines, each will serve as a virtual computer. And each computer will definitely have an operating system. It could be Linux, it could be Windows, it could be others. And also in each of virtual machine, you will pre-install a number of applications based on the request of the clients. So such kind of virtual machines serve as the fundamental idea to further expand to a kind of cloud computing paradigm. Then what is the purpose and the benefits of the cloud computing? The first of all is, as I have talked in the previous class, that for certain companies, the cloud computing will help those companies, as well as the company required computing resources, no matter hardware side or software side, there will be infrastructure less, okay? Which are system infrastructure dependent will be infrastructure less. So you don't need to own the physical infrastructure. You just pay as you go, okay? And that could save more money if a company is more a kind of entrepreneur company, or the company does not want to invest a lot in the hardware. But if you are a company that the data security is the top concern, then you probably need to invest your own computing devices or infrastructure rather than just using the cloud computing services, okay? So by using the cloud infrastructure on pay-as-you-go, all of us can save in capital and operational investment, okay? In general, yes. And the clients can put their data on the platform instead of on their own desktop PCs and their own servers. This is another hypothesis that if you have a cloud computing, a network of hardware and storage, it is better to store data there. That will be more reliable, okay? If you just put them in one of the own PCs, and when the PC becomes old, the hard disk could be broken in one day and you lose all the data. And the same thing applies to a server, okay? They can put their applications on the cloud and use the servers within the cloud to do processing and data manipulations. And next content is called cloud sourcing. And why is it becoming a big deal? Okay, so the cloud sourcing means you can outsource your idle resources to others. So the cloud sourcing would be very reliable because it uses a high-scale, low-cost providers. They are high-scale, low-cost providers. They can provide you probably much larger capacity with a lower price if they have a pooled resources. It is cheaper than you build up a new server or new infrastructure from scratch. Okay. And you can access those resources via web browser anytime and any places. You probably no need to go back to the office and sit at the front of the computer to operate. When you're walking, when you move, once you have internet, you have devices as the end channel, you're able to access those resources. And you can change those resources quickly, so rapid scalability. You can immediately reconfigure the infrastructure capacity you want. And it has incremental cost, and it has the low sharing, okay? So you can forget needs of those infrastructure sites. That means the need of like building up the infrastructure to focus on the local IT business you want to do if you are a software engineer. But cloud sourcing also has following concerns. First is its performance and reliabilities, okay? So its performance might not meet your requirement if the internet is limited, or you go into a region which has limited internet, and the reliability as well. And definitely you lose the control of the data and the service parameters. Okay, you cannot control, because people control that for you. And application features and choices could also be another concern, because they're hosted, okay? And interaction between cloud providers could be another concern. And there's no standard API mix of SOAP and REST in the cloud sourcing. That could be another concern. And last one is the privacy, security, compliance, and trust. Okay. So a lot of large companies, they actually exploring that if they are providing cloud services, because they don't want to waste their data storage capacity. They might have a huge amount of room of storing data, and this can be rent out to others. But the security will be the #1 issue, okay? So probably right now the security becomes a regional issue. The data is not allowed to move out the boundary, okay? But you can be allowed to store it somewhere physically within the border of the region. So it allows data to store remotely to be temporarily cached on desktop computers, mobile phones, or other internet-linked devices. And there are some companies, they have offered, especially Amazon, they have quite a number of different storage services, okay? And this is some specific statistic about the cost of using those cloud storage. So opportunities and challenges in cloud computing. So the use of the cloud actually provides quite a number of opportunities. The first one is enable services without any understanding and maintenance of the infrastructure. Okay, you don't need to spend that amount of money. And the cloud computing can work using economics of scale. So it has measure of charge, measure of usage. So it can work as kind of utility service. Okay. And its sharing economy essence actually have the characteristics of lowering the cost. And it can face a large volume of users. So it potentially lowers the outlay expense for startup companies. So they don't need to buy their own software or servers. Okay, no matter, can be in terms of either software side or server side. Some software can be very expensive if you want to buy a one-time license, but you might not need to use it for the whole life. You just need to use it for a while to solve some problems. Then you just using the cloud computing can solve quite a lot of things. And the cost will also be by on-demand pricing, okay? And vendors and service providers claim cost by establishing an ongoing revenue stream. And data and services, they are actually stored remotely, but they can be accessed from anywhere. This is also very nice, attractive features to users. So meanwhile, there are also some drawbacks which prevent people to completely favor cloud computing. The first of all is you don't have the full control. The use of the cloud computing sometimes indicates that you need to rely on others. And such kind of feeling could possibly limit the flexibility and innovation, okay? So for the large companies like Google or IBM, they might not concern about it because they monopolize the markets. They are bigger internet companies. But some other smaller companies who wants to make innovations, who wants to develop their business, they could concern about it. Because if you will worry, like if your business becomes very successful, then people will charge you more or may 3A you by limit your access to those resources, okay? So that could be a big issue, though. And some argue that this use of supercomputers is a return to a time of mainframe computing. The PC was a reaction against, okay? And security could prove to be a big issue. So we still don't know how safe the data could be guarded by the cloud computing services. Will the operators leak our data or some other kinds of? There are some similar cases, okay? And also, in some of the regions, the ownership of the data in cloud space is a little bit unclear as well. You upload there, the data sit there. People might use it without notifying you, okay? There are also issues relating to policy and access. So for example, if your data is stored abroad, and which data security policy that you need to follow. And what happens if the remote server goes down? Then how can you access those data? And there have also been cases that users being locked out of accounts and losing access to data. Okay. So the advantages of cloud computing. The first, you lower your computer cost. So you do not need to have a high power, high price computer, which will be very expensive in one-time capital cost, as well as your utility bill. The server will consume quite a lot of electricity and the bill could be high. And also, since apps run in the cloud, not on the desktop PC, so you don't need to have a very super processing power to execute the program. And you don't need to have a very large hard disk space to accommodate that software. We can use a compact, lower priced machine as a kind of device and interface to interact with the cloud resources. And if you are using web-based applications, your PC can be less expensive and might require smaller hard disk, less memory, but more efficient processor. Okay. And also your PC might not need to have a CD-ROM or a DVD drive because you are no longer to install the software from the hard disk, from DVD disk and the CD disk. Okay. You might have improved performance. So if your computer have fewer programs running or hogging in a computer memory, you will see your PC will be always fast. Okay. And there will also be less computing waste jammed in your memory, okay, and other channels. And computers in a cloud computing system boot and run faster. So because there are fewer programs and process loaded into the memory. And also we have talked about the software cost. So if you have the software, you use the software host in the cloud, it typically charge you less. Okay. So instead of purchasing expensive software applications, and you can use the cloud software, which will be cheaper. It will be better than paying for similar commercial software. Okay. And also the software in the cloud computing services could be instantly updates once the maintenance is finished. So you don't need to worry about like continually spending time on updating your software, downloading the patches and update your software and so on. And you can have improved the document format compatibility. So you don't need to worry about your documents, like they are not compatible to the latest version of the software if you put them on the cloud side, because they will be maintained by the updating at the back end. Okay. And also with the cloud computing, you are able to sharing and update the document simultaneously and keep a consistent format of the document as everyone access to the same document. Okay. Ideally, the cloud computing service provider, they have very large storage space. So you actually potentially can have unlimited storage capacity once you have sufficient money. Okay. And increased data reliability. Although there are security issues, but the reliability of the data storage is actually much higher because you have a network of computers and the data can be duplicatedly stored in different places. Okay. So that once a node fails, it can be immediately backed up by the other nodes. And cloud computing also have a universal document access. Once you have the internet, you can access the documents anytime and anywhere. And latest version I have talked about it. It is not just the software. It is talking about the document editing. Okay, so if you work together, you will always see the latest version. And you have an easier group collaboration because you are working on the same target. You don't need to send the files back in, forward and back, and so kind of. You will be device independent. Okay. So you will not be bothered a lot by the problems in a single computer or in a network. Okay. And you can move to a portable device, and your application and documents are still available. But the problem is, to enable a high quality cloud computing services, you actually need to require a custom internet connection. So the internet connection is number one important for supporting the successful cloud computing services. And no service, no connection, no internet connection. So as you might use the internet to connect to both of your applications and documents, if you do not have the internet connection, you cannot access anything. And that internet connection means no work, okay, and no communication. And it could be a big trouble. And it does not work well for the low speed connection as well. It will be very low efficient. Okay, you will not also not receive a high quality service. So features might be limited, but this could be changed nowadays. We have more flexible applications, configurations of the cloud services nowadays. So it can also be slow, okay, even with a fast connection. So a web-based application can be sometimes slower than accessing a similar software program because their way of communication is different. Accessing the code in the local disk is always the fastest, okay? So this is because everything in the program, from the interface to the back end, they need to communicate. So there will always packages sending back and forth. And also, it could be slow if the cloud server is running a backup, okay? And stored data might not be secure. That's a security issue, okay? So will it be only you can access the data if it is highly confidential, or other unauthorized users might also have some tricks to access your data? We don't know. And stored data can be lost. Although this is a very rare case, theoretically it shouldn't be, but sometimes it did. It could not be like 100% guarantee. So high performance computing systems, not sure whether you can use cloud computing to achieve a kind of high performance computing systems. It might not have the comparable performance as a physical high performance computing system sitting in your center. Okay. But it can be utilized to emulate in general PC and a relatively small scale server. And some other general concerns in the disadvantages of the cloud computing is each cloud system uses different protocols and different APIs. So you need to learn different cloud systems when you use them, like IBM, like the Azure, okay, Azure Cloud, Ali Cloud, they might use different protocols and APIs. The Amazon AWS and so kind of. So some reason cloud plus big data analytics in data science. So this will refer to some actually new ideas of computing, the framework. Okay. So the cloud computing can host computation, but rather than made efforts to push the data communication. If we have like different communication of data security issues in a different communication, then we will design the computing framework, okay? For example, the federated learning or transfer learning or some other concepts to fit into the class structure, okay? So we can just using cloud computing to grab the computed information, typically gradients in your learning methods, okay? And to update the models in the cloud. So based on such kind of data security guaranteed, for example, the federated learning framework, and new theories and applications can be developed under such kind of framework. Okay. So next, I'm going to talk about the Internet of Things. So any questions about the cloud computing? So cloud computing is more like a cyber-side infrastructure. No, it's a kind of infrastructure development for supporting the cyber side. Okay, it's kind of putting all the resources on the cyber side together. And the Internet of Things is another stream of technology. It might fit into the cloud computing infrastructure, but mainly it's about Internet of Things. It's about the instrumentation and centralization of the information. So the instrumentation means you have sensors. You develop different sensors for monitoring different targets. You can have sensors to measuring the electricity consumption in your house. You can have sensors in the vehicle, and the data will be transmitted to the cloud so that the transportation system will know each individual agent. Okay, and for the person, for example, your Apple Watch and some other similar devices to measuring your health condition, and other tasks like computers, animals. Okay, you can have different sensors that are collecting their information. So the Internet of Things is using internet to connect different sensors together. And these sensors are attached on different things. Then that's called the Internet of Things. So in the previous last generation, that you have a computer connecting to a network. Okay, you're using a computer, that's the Internet of People. So the internet connecting people around the world together into a cyberspace. And nowadays, we do have sensors. They call smart sensing system. They have the Wi-Fi function. They have the measuring equipment function. They're collecting the data. And they might have some edge computing power to processing and analyzing those data and later transmit it back to the cloud. So the definition of the Internet of Things. The definitions are also not fixed. There are different versions of the Internet of Things definition, but they could mean the similar things. So the Wikipedia definition of the Internet of Things is that the Internet of Things, also called Internet of Objects, refer to a wireless network between objects Usually the network will be wireless and self-configuring, such as household appliances. So one key important thing is the wireless network, okay? So if you have a smart sensor, you don't have a wireless network, the connection will not be true, okay? Otherwise, you need to require a physical lens to support the information transmission from one object to the sender, okay? So the wireless network is the fundamental support for realizing the Internet of Things. And WC's 2005 definition is like by embedding short-range mobile transceivers into a wide array of additional gadgets and everyday items, enabling new forms of communication between people and things, and between things themselves. So this sentence looks complicated, but it just means like if we give different objects a machine or a sensor or a device, which is able to collecting the information of that device and transmitting this information to other nodes or other objects involved in this Internet. And this could be called Internet of Things. So Internet of Things involve the information transmitted to different objects to humans, as well as receive some information from other places to that node to perform some analytics, okay? So if you want to develop an Internet of Things system, technically, you need to address the following problem. The first thing is, what are the objects that you want to measure? Or is everything you concerned that they need to be measured, or are they measurable? Okay. So what to measure, or you want to measure everything? And if you have determined what to measure, then you need to find out what are the suitable sensors. What kind of sensors do you need? And does the sensors have the Wi-Fi function? Is able to transmit data to the cloud, to the network? And also, are the sensors fitting the working environment? Is it durable? Okay, reliable, and so on. And you might also need to do a kind of optimization of the sensor location, because you have different sensors and they're connected. They work as a network. Then you need to optimize the sensor location in some space, and also design the sensing network. You also need to determine the data transmission protocol across the network, okay, so that you can at least have some communication standard and some security guarantee. You also might think of involving some of the edge computing devices. Sorry. This is because for some of the objects, the sense data can have large volume. It could be image. It could be huge amount of numbers, okay? Very large matrix. Then if you directly transmit them, you might require 5G devices, okay, 5G network system. Or you might require very wide broadband to support the data transmission. What if we don't have that kind of network condition, or we find out that it's a waste of resources? Then you might consider using edge computing to do the data processing locally, okay, and generating some of the results. And central system for information integration is needed for the Internet of Things. You need to fuse information from different corners to a center. And here, that's the place that cloud will play and participate. So how do Internet of Things affect your life? Okay. So it enables a lot of services become online and allow you to access the information of a lot of things that you might take time in reality to access. Because you can talk via the internet, a human can check the information of an object via the internet. That means you can access its information. Okay. So for example, the electrical appliances, if you have an Internet of Things system, you can schedule their operating time, okay? You can set them to work on, for example, 2 p.m. for cooking your coffee, a cup of coffee. And at that time, you just walk there and grab your coffee. You don't need to manipulate the machine and wait there. And for nowadays, electric vehicle, you can set up its charging time, because usually the electric vehicle will charge like, for example, hour from 0 to full battery tank. You can actually schedule its charging task until what kind of time, then you disconnect from the electricity power grid. Also, have a meeting schedule, smart meeting schedule. And there are also other ways. For example, online doctor and shop handle. So the Internet of Things actually introduced a new dimension to our real reality world. Besides the location and the time, you are able to access different things, and those things become a new dimension. It doesn't mean that in the past you cannot access those things. I mean, in this new dimension, you can minimize the distance as an instance via the internet if you have an Internet of Things connection. And why Internet of Things? What are the advantages introduced by the Internet of Things? First, the Internet of Things actually offer you a dynamic control of the industry and daily life. You have more frequent access to information. You are better to control and make a better decision. And you can improve the resource utilization ratio. If you know what are the spare items, what are the lacked items, you can determine the better usage of this one. And also an example is called smart refrigerator. So they use RFID to attach different items contained in a smart refrigerator, and this refrigerator will have a screen, an interface to display the items in it. Okay, is it fresh? And when does it produced? Is it going to be perished? That could be affect your decisions of consuming those food, right? And the Internet of Things offers a better relationship between human and nature. You get more information, you will know how human behaviors will affect nature. And forming an intellectual entity by integrating human society and the physical systems, make the whole ecology smarter, okay? And also flexible configuration. You have different informations, then based on your different needs, you can make a better configuration. And it offers a universal transport, internet working, not just between humans and also among humans and things. It offers a higher accessibility and usability to those things. And the development of Internet of Things actually have experienced many years. So in 1997, the Internet of Things is the 7th in a series of ITU Internet reports originally launched in 1997 under the title Challenge of the Network. At that time, people were already thinking about like using the Internet to connecting things and human rather than just among the human. Okay. And in 1999, the Auto ID Center, founded in MIT. In 2003, the EPC Global, founded in MIT. In 2005, 4 important technologies of the Internet of Things was proposed in the WCS conference. And you must be very familiar with them. The first one is called RFID. And nowadays, RFID is everywhere in the supply chain. And the nano, and the wireless sensors, and smart tech. Okay, they are all becoming true nowadays. In 2008, first international conference of the Internet of Things, the IoT 2008, was held at Zurich. So nowadays, the connected objects over past years, more and more objects now are connected via the Internet. Okay. And this is the scope of the Internet of Things. So it connects buildings, energy, consumer and home, healthcare and life, science, industry, transportation, retail, security, public safety, IT and networks. And the further sectors under each of the sectors, okay, different application groups, and further locations and devices for connecting those things. And one good application or very influential application of the Internet of Things is kind of after the Fukushima disaster, compatibility. Okay. So we have different sensors for measuring the radiations across different regions. Then we'll easily tell people where the places that the radiation are going to 3.8, okay, and can help people to do a better preparation and evaluate the severe level of this disaster. And many people connected radiation sensors. It could help the whole world to verify the true level and the true data. For example, if we want to make sure our air quality is good, so I have one watch might be able to sense the air quality, and you might have one. Then there are also Hong Kong Observatory. They have data. And if we have all different data collected and crossover, we will validate whether the authority is reliable or is true. Okay. All right. So we probably will take a break, 15 minutes break. Then we come back at 9. Then we connect. We continue. Okay. Okay, so wait, let me full screen this one. So we have talked about one nice applications of Internet of Things, and another thing is kind of in the business side. It's a M2M scenario, which use the smart ice cream cabinets to measure the quality, actually to real time monitor the quality of its ice cream products served in the ice cube. Okay, so the application actually provides consumer products companies with detailed information about location and status of its ice cream cabinets, and the information can be used to find these cabinets. They will say, okay, how many inventories are actually remaining there, and are there any types of products actually are short of supply, and is the temperature of the ice cube good to maintain the quality of the products, and so on. The information can be collected to make the supply decisions, as well as immediately find out there are any irregular service states in this network. Okay. And in these ice cream cabinets, the sensor inside is utilized to get information of whether there are stockouts, need to fill any new products, and its location, so that you won't miss anyone. And also the temperature, power supply, they're consistently provided, they're good, and other behavioral statistics. Okay. So basically, the Internet of Things will be more and more appeared in our daily life. And it is a very general term and framework, but in general, it represents a kind of infrastructure of networked sensing. Okay, so it targets on sensing systems, networking systems, and information systems. And the IoT technologies can be a great generator of data. And the data generated by the IoT technologies can be further utilized to do data science, okay, and to develop some AI techniques or AI-enabled services. And if you guys look at nowadays vehicles, it will soon become another type of node in the IoTs. And the vehicles with more and more like computerized and with kind of network connection. In the future, you are able directly to use your vehicles as a communicating environment, entertaining environment, okay, in the future life. So the IoT technologies can be application driven, but simplest. Usually it deploys a set of sensors, collecting data, and centralized information. And this IoT technology are usually more hardware side. Yet it forms a foundation for building the cyber worlds on top of the physical systems. And it serves as a communication between the cyber physical worlds. Okay. And it also involve edge computing and cloud computing. So if we compare Internet of Things and cloud properties, we will find out the cloud service focus on the virtual world, and it talks about like the big things, the large scale services, and emphasize on its unlimited capability and very strong availability of different resources. And the Internet of Things actually rooted in the real world. It targets on a large number of small things, and it has constrained devices, and it faces the reliability problem. Okay. All right, so the lecture 1 will be stop here, and we will move to our lecture 2, the process engineering and systems modeling. So a lot of engineering sides in data science and applying data science into the development of smart city is higher level. Philosophy is more like a process engineering and systems modeling. So given a system or given a kind of a network, and you need to identify what kind of data you need to collect. What is the dynamics behind it? Then you need to have a systematic way to think about, to analyze such kind of targets. So the fundamental question will be, what is the process? What is the definition? So we're using the solitary pulmonary nodule diagnosis process as an example. So we brief it as an SPN. So in this SPN diagnosis, we will find that the whole procedure can be described as a process which take a certain inputs and make certain number of decisions and generate outputs to the next flow. Okay. So this SPN diagnosis will take the first input, which is called Cx-ray 1. So it will read the Cx-ray 1. Then you set a kind of criteria to judge or to decide whether it is an SPN or not an SPN. So if it is not SPN, then you go to another decision node to judge whether that patient is normal or that part is normal or abnormal. Okay, so Cx-ray refers to chest X-ray. Okay, and the CT, the computerized tomography, refers to CT, and F/U means follow-up. Okay, so if you decide it is quite likely SPN, then you further input the clinical information to produce a clinical cognitive evaluation. Okay, and this process, its outputs will also be fed into a decision node. So it determines whether it is benign or not benign. Okay, so if it is benign, then you have a standard follow-up. Or if it is not benign, then you need to have another decision-making node. Okay, so the upper bound, the upper arm of this node says like we need to feed the old chest X-ray data into these not benign results to evaluate the previous chest X-ray data. Okay, then we will determine whether it is benign or not benign. So if it is benign, then you need to suggest a 1-year follow-up. So it is not benign, then the previous is also not benign, then you need to do a CT scan, and you need to evaluate the CT scan and to make a further decision whether it is benign or not benign. So if it's again not benign, then you need to involve the physiological data to do a diagnostic test selection. So benign or not benign at this stage will be fed into the further process A and B, which described in the next logic map. It is more complicated, involves a lot of logic. But the good thing is if you follow the flow chart, which is utilized to describe the whole process, you will clearly understand the logic of decision making. And you will clearly know how the results is generated and why should we do that? Okay. So this is the value of the process engineering, and the systems modeling is typically down from the process engineering perspective. So for your project, if you identify a problem, then one important thing is you need to understand the whole process and its dynamics. So very important thing is, what does this process take as input? And what does this process produce as output? Then you will know what are the input attributes, and what are the data you need to collect, and what is the response, what is the target in the machine learning or data-driven model. So the process engineering, the process is usually considered as a collection of events, actions, and factors, as we said, as we illustrated in the previous figure. Okay, so different events means kind of data or evidence you obtained, and actions is the decisions you made based on analyzing the data and based on the rules, and the factors are the results, or kind of like this. And the more examples of the kind of process engineering in real application. For example, we go to a factory, we look into the manufacturing process. We see that workers, they are taking something and feed it to the machine, and the machine, after a number of time, then it generates some of the products. Okay, so such kind of manufacturing process, it also can be interpreted with such kind of flow charts to describe the different stage of process actions and decision made, and so as the design and business process. So there are different types of the process, and in generally, the process type can be categorized with two ways. The way one is based on whether the process is structured or unstructured. Okay. And also, the second way is you can determine whether the process is deterministic or it is stochastic. So deterministic means you fit in something, you will produce something out. Okay, without any surprising, without any changes. And stochastic is purely random. You don't know what will be the outcome. Okay. And structured and unstructured process means, structure means it's very systematic. You have different steps organized in order. And unstructured means the different cases could be different. Okay, like healthcare, different people can be different. So using one process flow might not describe all the case, or different data collected, evidence collected, you cannot generate one process flow to describe it. So there has been a number of process modeling methodologies, and some are already very commercialized as a software. Okay, so I don't want to follow each one of them, but you just need to know it. And the IDEF methodologies in the very end is one very popular technique utilized in process engineering. Then the question is, what is more important? So is it the modeling tool itself important, or the user familiarity with the tool is important? Okay. So these introduce the different level of the IDEF methodology, which is IDEF means integrated definition. So there are different versions of IDEF. Okay. It interprets different functions or capabilities of doing the process engineering. So the IDEF 0 indicates the methodology just focus on modeling a wide variety of systems, which use hardware, software, and people to perform activities. And IDEF 1X means to schematically model relationships between various pieces of data. And the IDEF 2 aims to capture the dynamic behavior of a system. And IDAF3 is commonly utilized, most commonly utilized, or most classical one. It created specifically to model a sequence of activities involved in a process. And IDAF5 aims to model domain ontologies, and IDAF6 aims to define the motives and that drive the decision-making process. So the IDAF3 process model looks like this. You have a number of rectangles. They serve as kind of different activities or behaviors, okay? And you have different nodes as logic links, okay? They actually reflect the decisions, okay? So under the activities, there are the links which describe relationships between activities which are of three types: precedence links, relational links, and object flow links. And these activities, they have different meanings. And for this process, the beginning is, okay, we start from planning and we apply a logic function, which is all. So either you do design one or you do design two. And based on either of the designs, then we do the evaluation of the design. Okay. Then we exclusive OR, which means we cannot go both links. We can just pick one of them to go. We either revise the design or accept the design. So this is a kind of process model. So there are also another type version of the process model is you can add annotations to the nodes in the process model. And this is kind of input-output model, okay? And for decision-making logic. So you have like I1, I2, and into this decision-making nodes, and experience a process with condition 1 and condition 2, C1, C2. Then into another decision-making, then you output the output 1, output 2, output 3. So this O node actually can contain multiple rules for decision making, or can describe a more complicated logic. And those logics are actually a set of if-then rules, which depends on the previous conditions and received inputs. Okay. Then what is the difference between process and system? So the interpretation, so there's no clear boundary of saying is process a larger scope or systems larger scope. So interpretation can be made from multiple aspects towards these two terms. So if the system is very specific mechanical or electrical components which utilized in some processes, then we will say process includes some of the systems. And if the system means a higher level scope, then it will be regarded as a collection of process which transforms a set of inputs under certain conditions to a set of outputs. Okay. And systems modeling. And this term utilized, so this systems modeling term have been utilized in different fields. So either in mechanical engineering, in physics, in electrical engineering, in control. And sometimes people are mainly concerned on identifying the system dynamics through the modeling. And the model types involved in system modeling can also have multiple types, including the ODE, which is ordinary differential equation, the PDE, partial differential equation, the state machines, and the hybrid of them, and etc. And the modeling approach mainly refers to two directions. One is called white box approach. That means you have explicit mathematical expression, which is physics-based models. And another is called black box, which is you know the input output, but you don't know the explicit dynamics. But you use some techniques to approximate, to identify. And sometimes in the control field, it's called pattern recognition. So system dynamics models, people will typically say model is a mathematical representation of a system. Okay, we aim to develop a mathematical representation to simulate or mimic the system. So the model allows simulating and analyzing the system, while the models are never exact. So there will always be the problems, or you cannot model all aspects of a system. You're unable to do that. So there are always room to improve the system modeling methods. And also the modeling really depends on your goal. You don't need to develop a perfect model. You need a model to address your problem, okay? So a single system can have many models, and you need to always understand what is the purpose of that model. So large libraries of standard model templates exist, okay? So you can, just pick one of them based on your needs of the modeling task and apply them. And what is innovative part is a conceptually new model, and it is a big deal, okay? So we look at an example of the traditional Pde model, which include functions of spatial variables. So it is widely utilized in electromagnetic fields, mass and heat transfer, fluid dynamics, structural deformations. So examples of sideway heat equations can be look like this. Okay, you take derivatives. And what is a black box model? So you don't have that explicit mathematical equation here, but you know what is the input and you know what is the output, and you know the internal state. And the black models actually describe P as an operator. Okay. And this P in AA, aerospace and mechanical engineering, physics, refers to state, space, and utilized to ODE and PDE. And EE refers to a black box. And the chemistry engineering actually use anything to do this. And CS to develop this P, actually we use state machines, probabilistic models, or even neural networks. And that involves using data to estimate this P or to identify this P, which is actually data-driven modeling. So black box model from data. So in control, due to the system complexity, so exact form of models or deterministic form of model parameters cannot be easily obtained. Therefore, based on the system observations and responses, we need a new direction of determining the black box. And here, the model identification from data starts to be investigated. However, in control, a lot of times the structure of model to be identified is typically assumed, while the estimation focuses on the model parameters or a number of assumptions is applied into the problem. So process models, we typically have two types of analysis of the process models. So if you have a process model created through a modeling effort, is referred to as an as-is model, the process as it is. And such model needs to be transformed into a more complex form, which is to-be model, which meets the goals of the re-engineering efforts. So to perform such kind of task, there will be two types of analysis. One is called computational analysis, another is called observational analysis. So observational analysis is pretty straightforward. You use your eyes to observe and think about a way to reducing the redundant activities. Okay. So if you look at this process, see activity 1 takes some inputs and based on some conditions and produce the output. You will see that such kind of process, such kind of activity, its input, output, and conditions, they're exactly similar. They might have different values over time, but their structures are similar. So they can be merged as one, okay? So you can eliminate the redundant activities for your observation. You can also, if they cannot be duplicated, has a little bit different. You can merge of serial activities as a new one, okay? Where something can be changed. You can also eliminate the cycles if you think these cycles is not necessary or does not engage the main process of this one. Okay, so you can eliminate activity 3, which is a feedback adjustment. Okay. And the question is, what is the end result of observational analysis of a process model? So we basically, the re-engineered to be process model needs to contain normally less activities than S model. That means we want it to be more compact, okay? And we aim it to have a better performance, which has a shorter process cycle time. And sometimes this issue can be better addressed via computational analysis, okay? And this computational analysis will involve some algorithms. Let me see. Yeah, I think we have sufficient time to finish these algorithms, okay? So assume that we have a graph representation of dependencies in these process models. Look at the left side. It's a topology. It's a diagram of activities and the corresponding incidence matrix, which listed on the right. Okay. And you will see that 1 is pointed by 2, by 7, by 6. Then you will see there are star 2, 6, 7 indicating in this matrix. And if you look at the second row, you will find out the 2 is pointed by 4. So state 4 pointed to 2, and there's a star here. So you get this such kind of incidence matrix. So there's another kind of convention. It will be like this, okay? So you have inputs to activity J, and you have outputs from activity J. And you can have another interpretation. You say succeeding activity J or preceding activity I. So there are different interpretations. So based on the ordered incidence matrix and the corresponding diagram, we want to reorganize the topology to make it a clean process, very compact, but without losing the logic. Okay. So basically, the computational analysis means like we're given the input of the topology and the matrix, then we will generate a better matrix which have a better organization, equivalent organization, but with a more compact shape. So this soft computing algorithm we introduced is called, case one is called organizing non-cyclic graphs. So non-cyclic graphs means there's no circles here. So if we have such kind of topology which fits the case one organizing non-cyclic graphs, we can introduce this the topological starting algorithm, TSA. So the TSA step one, set I equal to 1, which is the line, I guess. Then you draw a horizontal line through the unlabeled row K of the incidence matrix with only one non-empty element. Then you draw another vertical line through column K of the incidence matrix. Then label I the cross-out row K and column K of the matrix. And if each row and column of the incidence matrix has been labeled, then you add I by 1, then go to step 2 and repeat until the algorithm ends. So we use a very simple example to illustrate this process. Assume we have such kind of incidence matrix and a corresponding digraph with 4 vertices, 1, 2, 3, 4. Then what should we do? Okay. The first iteration of the topological sorting algorithm is we find a line I. We need to set the iteration I. Sorry, this I is not line, it's the iteration. So the first iteration, we draw a horizontal line to unlabeled row K of the incidence matrix with only one non-empty item. Okay. So if you see here, so we first draw this one. Okay. Then we take a vertical line. And in the second iteration, we move to the row 2, we draw a line and draw another line, vertical line. And we repeated this and until the whole iteration is finished. Okay. So you can see that in this process, we first draw 4 and we take a vertical line. Then we see the remaining 9 cells, 1, 2, 3, 1, 2, 3, 9 cells, and only 2 has no these stars. Then we draw. Okay. Then for the remaining 1, 2, 3, 4, then we find 3 does not have star. Then we draw a horizontal line. Then we draw another vertical line. So this is a way of implementing this algorithm. Then based on this order, we can reorganize. Okay. So we see the iteration 1, 2, 3, 4, and it's reorganized order. Then we switch. Okay, we reorganize it with 1, 2, 3, 4. Then we will have a new matrix, which is like this. Okay, it's actually 4, 2, 3, 1. Then we have a reorganized matrix. Then we have a new arrow topology, the digraph. Okay. So based on the previous example, it is clear that due to the increase of the system or process complexity, the chance of obtaining an exact parametric description of the system or process is pretty slim. So we have to obtain an approximated presentation of a complex system or process. And here is where the data-driven approach applies. And the conceptual idea is we believe that data is a replication of the physical world. That means all the data, we can treat it as a digital replica of the real world. And we assume that we don't have any clue of the mathematical presentation of a system and process, but we have observations of their inputs and outputs. And the whole data-driven modeling process is always formulated as identify the mathematical relationships by applying the machine learning algorithm into data sets of inputs and outputs of a system. Okay, so some real examples here. We use wind turbines as an example. It's a wind energy conversion system. Okay, so we have the wind as the input, which it brings its kinetic energy, and we use a rotor and the blades to swap and absorb the kinetic energy in the wind, and using the drivetrain to lead the gearbox, and from low speed to a high speed, then lead the generator to rotate and generating electricity power. Then what should we do to the modeling the wind turbine energy conversion process? We need to know what is the input, what are the control settings, control parameters, and what is the output. And then we identify the mathematical relationships among them. Okay. Another example is the combustion system. So in the combustion system, we know that we need to burn. Okay, we need to fill in the materials to burn, to make heat, which the heat will utilize to do other purpose. Okay, so you need to decide the bells and the bulk, as well as the primary air, secondary air, inject into this combustion system. And you typically treat the efficiency as its output. And the whole dynamics is quite complicated. You cannot have exact physics to describe it. But we can have observations of data collected from this system. And we are able to, using those data, to approximately identify the mathematical formulations behind it. And the last one is the building as an example. Okay, so you have different electrical appliances involved in this building, and this building is connected to a grid. And what you want to control is the heat, ventilation, and air conditioning system, HVAC system. Okay, which utilize to cooling and heating the whole building. So you need to collect, you need to deploy the IoT system, collect information from different corners, different aspects in this building. And based on the collected data, you need to do the data-driven modeling. And for this such a kind of complicated system, you surely won't be able to have an exact representation, mathematical representation. So the complexity typically in real problem comes from first a high dimension of system parameters and a strong nonlinearity in the process, as well as the domain knowledge in the system sometimes is not even limited, it's unavailable. Okay. And in data-driven modeling, the main questions that we need to answer before doing the data-driven modeling is we need to first identify what is the level of the domain knowledge and how does the domain knowledge can be useful to our data-driven modeling task. And the second is data availability. Has the data been available to solving this problem? Has the data been collected for this problem? And based on the collected data, next you need to identify the useful attributes involved in the data-driven modeling. For example, for a process, the data set might contain many attributes, but you need to identify some of them which refer to inputs and some of them refer to outputs. And next, you need to address the modeling problem formulation and the modeling algorithm selection and modeling results validation, and so on. Okay, so I guess that's all for today. And I thank you very much for your time. And I think we will stop here. And I will see you guys next week. And we will do some technical review of the classical machine learning techniques, okay, or data mining techniques. All right, thank you, and bye-bye.